All right, today we are on the hunt for the sweet spot. You know, that perfect little zone where a whole bunch of different rules and conditions all line up just right. And believe it or not, we're going to find it by drawing a map. So let's kick things off with a puzzle you've probably run into. You see an ad for a big shoe sale. Seems simple enough, right? But wait a second. If you look closer, there are a bunch of rules. There's a price range for the shoes themselves, and there's a range for the discount. So if you've got your eye on a $50 pair of shoes, what could you actually end up paying? Don't worry, we're going to figure this out for sure. Okay, the tool we're going to use to solve this has a bit of a technical name, a system of linear inequalities. I know, that sounds super complicated, but stick with me. It's really just a fancy way of writing down a bunch of rules, kind of like the ones from that shoe ad. Think of each inequality as just one rule in the game. And here's the absolute key to the whole thing. A solution here isn't just one single number. It's any combination, like, say, a regular price and a sale price, that follows all the rules. You break even one of those rules, just one, and you're out. It doesn't count.
So you might be thinking, okay, how do we actually check if something works? That's a great question. Before we go and draw these big, kind of complex-looking maps, let's just start small. Let's figure out how to test a single possibility to see if it plays by the rules.
Okay, let's take the point 1, 0 and see if it fits into this system of rules. All we do is plug in 1 for x and 0 for y, and just check them off. Rule 1, is 0 less than 4 times 1? Yep, 0 is less than 4. Check. Rule 2, is 0 greater than or equal to 1 minus 1? Well, that's 0, so yeah, it is. Check. And rule 3, is 0 less than or equal to 2 times 1 plus 1? That's 3. Yep, check again. See, it passed every single test, so 1, 0 is officially a solution. All right, now let's try a different point, -2, -8. First rule checks out, no problem. But then we get to the second one. Is -8 greater than or equal to -2 minus 1? That's -3. Uh-oh, no, -8 is definitely not greater than -3. And that's it. Game over. As soon as you break one rule, you're done. We don't even care about the third one. That point, -2, -8, is not a solution. So checking points one by one is fine, I guess. But what happens when there are tons of solutions? Maybe even an infinite number of them. We can't sit here all day checking every single one. No way. That's why we need a better way. We need to draw a map that shows us every single possible solution all at once. You know the best way to picture this? Think about those old school overhead projectors teachers used to have. Imagine you have a bunch of see-through plastic sheets, each one a different color. Each rule we have gets its own colored sheet, and we shade in all the parts of the map where that rule works. So really, it all boils down to a simple two-step process. Step 1, for each rule, you graph it and shade in the whole area where that rule is true. Step 2, you just look for the part of the map where all of those colors overlap. That messy, multicolored patch, that's it. That's your solution. Okay, enough talk. Let's actually build one of these maps right now. We'll use a system that's got 3 different rules we need to follow. Okay, first up, rule number 1. Y has to be greater than -2x minus 5. So we start by drawing the line y equals -2x minus 5. And notice it's a dashed line. That's super important because greater than means the points right on the line don't count. Then, since y has to be bigger, we just shade everything above that line. Boom, that whole shaded zone is where rule 1 is happy. Now, let's bring in rule 2. Y is less than or equal to x plus 3. We draw that boundary line. But this time, it's a solid line. Why? Because of that or equal to part. It means the points on the line are totally included. We need to shade everything below it. And look, check it out. You can already see this new little area where our first color and our second color are starting to overlap. And for the grand finale, our third layer, we add the rule y is greater than or equal to x minus 2, another solid line, and we shade everything above it. And there it is. That's what we were looking for. See that triangular region right in the middle, the place where all 3 of our colors are mixed together? That is our sweet spot. That is the solution space. Every single point inside that triangle works for the entire system. Okay, so now that we know how to draw one of these solution maps, we have exactly what we need to go back to the beginning and finally solve that shoe sale puzzle. First things first, we've got to translate that ad into math speak. Let's say x is the regular price and y is the sale price.
Okay, the regular price part is easy, right? The ad said it's between $20 and $80. Now, the discount part is a little tricky. It says 10 to 60% off. Well, if you get 10% off, you're paying 90% of the price. If you get 60% off, you're paying 40%. So that means the final price Y has to be somewhere between 40% and 90% of the original price X. Okay, there we have it, 4 rules. So now we do the exact same thing we just practiced. We're going to layer each one of these rules onto a single graph and map out every single valid possibility. And bam, there it is. That shaded shape is the official sweet spot for the shoe sale. Any point you can pick inside that region represents a real combination of a regular price and a sale price that perfectly follows all of the store's rules. So let's get back to that original question. What about that $50 pair of shoes? Well, we just find 50 on the regular price axis, that's our x-axis, and we look up at the shaded area. Hey, look at the point 50, 30. It's sitting right there, smack in the middle of our sweet spot. So the answer is yes. A $50 pair of shoes could totally cost $30. That's a 40% discount, which fits the rules perfectly. Now, this whole method is way, way bigger than just figuring out shoe sales. You'll find these kinds of solution maps everywhere, in all sorts of fields, anytime people need to figure out what's possible within a set of rules. But this all leads to a really interesting question. What if the rules just flat out contradict each other? What happens if you draw your map and the shaded areas never actually overlap? For instance, take a look at a system like this one. You've got one rule that says y has to be greater than some line, and another rule says y has to be less than a different parallel line below it. When you shade both of those in, you can see they're shading in opposite directions. They're like two ships in the night. They are never, ever going to cross paths. And in a case like that, the answer is actually really simple and kind of brutal. There is no solution. There is no sweet spot. The rules make it impossible to win. It's just not possible to satisfy everything at the same time. And that really drives home that this isn't just some abstract math thing. Businesses use this to find the most profitable way to make things while staying within their limits. It's the same kind of thinking that defines the strike zone in baseball, or the exact right water temperature and pH for keeping exotic fish happy, or even just you trying to figure out how many snacks and drinks you can buy for a party without blowing your budget. So that leaves us with one final thought. Your own life is basically a giant system of inequalities, right? You've got constraints like your budget, the amount of time in a day, your own personal goals. So if you were to actually sit down and try to map all of that out, what would your solution map look like? What rules are defining your world?